Bom dia aqui, boa tarde, acho que estão aí. Meu nome é Leonardo Marques da Cruz, eu sou oceanógrafo, sou formado pela Universidade do Estado do Rio de Janeiro, tenho mestrado na Universidade Federal do Rio de Janeiro, em engenharia civil, com ênfase em engenharia ambiental e modelagem computacional, e atualmente sou aluno de doutorado na mesma instituição, só que no programa de engenharia oceânica. O que eu vou apresentar aqui para vocês é a nossa experiência dentro da PROOCEANO, que é a empresa que eu trabalho, com o uso de veículos autônomos marinhos, os chamados gliders, e como a gente vem utilizando esse tipo de equipamento em águas brasileiras. Eu vou pedir permissão agora para trocar para o inglês, para a gente poder entrar realmente na apresentação, ok? So, as I told you, we've been presenting what we've been working on PROOCEANO related to gliders and robots, mostly in accordance and with relation to the oceanographic operations we've been performing in Brazilian waters, right? So I'll go very briefly through the PROOCEANO history, and then I'll change into the very subject of this presentation, which is the gliders, the robots that we've been using, right? So the company was founded in 2004, and at that time we were pretty much focused on the because in 2000 the oil and gas market was open in Brazil, so there was a lot of companies coming to Brazil to operate and to explore oil in Brazilian waters. So at that time there was a huge demand for oceanographic services and applications to subsidize this activity, right? So we were a spin-off from some university laboratories, and at that time we were mostly doing numerical modeling and data analysis. I mean, always related to the oceanographic field, right? We were at that time finishing our masters and PhD, and I mean the four of us. I will present it to you later. And we decided to start a company and to try to provide such services to the market that was growing at that time. So it was four guys. I mean, it was me, Julio, Francisco, and Mauricio, and we started from scratch, basically. And since 2012, we became part of an international group, which is the CLS Group, a French group based in Toulouse, which is a subsidiary of the French Space Agency, right? As services, we are focusing our activities in operational oceanography, mostly ocean forecasts, but not only ocean forecasts, but also applied ocean forecasts to subsidize and to support action related for planning in case of marine accidents and pollutions and everything, and also for search and rescue at the sea. We do a lot of environmental monitoring, also numerical modeling and data analysis, as I told you. This was our pretty much first area of expertise. A lot of data visualization and integration, some environmental risk analysis, and research and rescue projects where we can test new technologies, which is pretty much the case when we started to use gliders, right? So in terms of numerical modeling, I mean, this is the type of service that we provide. Normally, we are modeling the hydrodynamics of the area that the client has interest in. It can be to subsidize any activity in the area, or to forecast, as I previously mentioned to you, right? Those are some examples. I don't know if you can see the mouse, but those are some hydrodynamic modeling that we've been performing, different time and spatial scales, as you can see, from very, very shallow waters inside bays and channels up to the Atlantic basin, right? This is mostly done to get and to achieve ocean forecasts, but also to subsidize oil spill modelings that will support offshore drilling operations, right? So those are another examples from oil spill modelings, but blending with the biological and the environmental information from the area. And the main purpose here is to combine a probable area of oil to reach and to check and to evaluate against what we have in terms of the environmental components in the area, and try to achieve and to quantify, I mean, the possible impact of an oil spill, right? And then once we were growing as a company, we started to bring some technology to our portfolio of services, and that's how we started to bring some equipments. In the very beginning, I would say back in 2007 and 2008, we started to use drifters, and then we moved to profilers, which led us to classical oceanographic mooring lines, and also gliders, which is our main subject here, right? The way I brought this information in this historical line is that why we decided to use gliders and drifters and floats, basically to improve our skills in forecasting and diagnosing the ocean, right? So those are some examples from classical mooring lines. I don't know if you are familiar with that. Those are fixed mooring lines that you deployed in the water and start to collect data from currents, temperatures, salinities, it depends, right? So then we are reaching to the interesting points. So based and with all this technology, we blend it all together and develop some systems to subsidize and to support offshore operations, as I told you. So here we have an example of a product, a service that we call SpillTrack. And then in these services, we blend satellite images, in situ data collections with different platforms and modeling. And the main purpose is to forecast the ocean and to support drilling operations. We have a similar service, not targeting pollutant and oil spills, but for search and rescue. If you have some accident with equipment and men at sea, we have some modeling, some models that has the ability to try to predict or forecast and to help, I mean, the search and rescue operations, right? So those, I mean, I went pretty fast on these because now we will jump into the glider experience that we have, but mainly the usage that we have for the robots, for the glider, is to improve our skills to forecast and diagnose the ocean, right? So here we go. Now we get into the main subject of this talk, right? We used to call those equipments like autonomous vehicles, right? That's because they can be in different models and shapes and piloting techniques, right? I'll go through it very briefly right now. So basically those gliders are robots, right? So they navigate, they drive, they fly, or, I mean, in general, I mean, here, the robots. And here is the first main characteristic of the equipment that we've been using. It has no demand with permanent interaction with a human operation. What I mean is that they can receive the order, they can receive what it is supposed to do, and they can get really pretty well without the human operator, because the navigation system, it carries on board a very sophisticated navigated system that can deal pretty much good with currents. I mean, the type of the robot that we've been using, it even doesn't demand the permanent connection with the pilot, but also it can connect with the pilot through satellite communication. With it allows the equipment to have more autonomy and to operate for more time with a reliable data collection, right? Regarding the payload, such equipments can carry a variety of sensors depending on the application. I mean, it can measure a bunch of parameters from temperature and salinity to turbidity and dissolved oxygens and oxygen, sorry. And it basically, it's a ratio. The payload, you can carry several sensors. It may, of course, it will affect the endurance of the vehicle, but then this is the good part of the planning the missions, because you can evaluate what you need to actually collect, right? So those are some examples, right? This is something that in the oceanographic field, this is a very, very good picture because it's, I don't know if you are aware with that, but it's very, very difficult to sample the ocean, right? I mean, there's a lot of logistics issues to keep a vessel on the sea. It's very, very, very expensive. And then, so collecting data in the sea was actually is always a challenge, right? And here is where the magic starts. I mean, if you keep, we are going to talk about, we will forget about vessels and robots or equipments that are connected to the operation through physical connection, right? We will focus our conversation here on the small ones, the ones that has no connection and are prepared to do well at sea without a permanent connection with a human operation, right? What those robots, they brought, it was a game change in the oceanographic sampling field, because basically by using them, we can widen a lot the sample universe. So basically we change the way we used to sample the ocean, right? Normally the classical way was to deploy fixed instruments. It could be a mooring line. It can be, it varies. Then we get the drifters where we have no control. The drifter starts to drift and it can acquire information from the ocean. And then the floaters, the profilers. But now we have, finally, we have a vehicle, an autonomous vehicle that can dive and can fly in the ocean for several weeks up to, I would say, a couple of months, collecting data in the ocean in a 24/7 basis. So this was completely new, right? Another point that is important to mention here is that when you have a vessel and you are supposed to deploy equipment in the ocean, you need to get rid of the sea state. I mean, it's not every time that you can deploy operations equipment at sea without risk. I mean, sea state is very limiting the data collection at sea, the classical data collection at sea. And with those robots, basically, I mean, the underwater ones, I mean, the ones that dive, the ones that we are talking here, the gliders, you don't have this issue, right? Another aspect is that the moment you collect the data, I mean, the glider, it dives, and then it goes up. And the moment it reaches the surface, it transmits the data. So it's almost real-time data. And the risk of losing data is very small, I mean, since it transmits from time to time. And as I told you, the main advantage of these systems is to widen the spatial and temporal coverage of the data that you are collecting, right? Another important point that such technology brings to us is that it reduces a lot the vessel usage. And in the end, it reduces the cost of the operations and also the risks of the operation. So that's why we are, that's how, as a company, we are managing to bring such new technology into our portfolio of services, because to fly gliders at the sea right now, it's still new, but people are doing that everywhere in the world. But to bring such equipment into a regular service and to provide operational services with such equipment, it's quite new. And this is how we've been getting the big thing. This is how we are getting advantage of these such equipments, because we can lower the operational costs and we can lower the risk. So this is a win-win situation, right? Here I brought you some pictures of the equipment because at that time I'm almost half an hour speaking about this equipment, and you haven't seen that. So this is how it looks like. I mean, the sea glider, right? Here, this is basically this equipment. It converts its vertical displacement into horizontal movement, right? Because it has no power engine. I mean, no propulsion, right? It's like a glider. So basically, it changes its weight. I mean, and then it dives. Once it dives, it has heave, pitch, and hold, and then it can control the dive. I mean, actually flying in the sea. This is how it works. So to do that, I mean, such model, right? The sea glider, it needs to convert the vertical displacement into horizontal displacement, so it needs to dive. So the deeper this equipment dives, the better is the conversion, and more optimal is the dive and the displacement and the dive and flying at the sea. So what we've been experiencing is that our model, there's other models with propulsion and that can adjust if you need to collect data in such shallow water, but our model, it needs to, I would say that it works well from a little bit less than 200 meters up to 1,000, which is the operational limit of this equipment. Right now, the manufacturers, they are working and they do have some plenty of options in terms of gliders. I mean, if you need to dive in shallower waters, or if we need to dive more than 1,000, you can adapt and you can bring, you can choose different models, right? And for us, for the oceanography community, it's straightforward to see the advantage of such equipment. For example, here is an example. Here, this is the Rio de Janeiro coast, right? This is Guanabara Bay. I mean, it's with a little bit of imagination, I think you can see that. So this is the Cabo Frio area, and this is the continental shelf, right? I would say that this is the 200 isobathymetry line. So the glider kept flying from here to here. I mean, it dives constantly and it samples the ocean here with a lot of parameters. So this is an amazing data set. And if you were supposed to do that with a vessel, it would cost a fortune, right? So, and then we bring into the real data world, right? I will present you some results and some experience with real projects, both from research and development projects and for operational projects, right? So since 2012, when we started to use gliders, actually we started to prepare ourselves to use it from 2010. And by 2012, we were actually ready to fly our first glider in the ocean. And it started in a project called Projeto Azul, which was an R&D project sponsored by BG. Now BG was bought by Shell. And then at that time, we started a 3-year project flying not only one, but at that time, the plan was to fly 3 gliders in the sea and to achieve and to get information from several equipments. And basically, from 2012 that we were ready, we started March in 2013. We have accomplished 50 missions with gliders, basically sampling temperature, salinity, dissolved oxygen, chlorophyll, turbidity, and also passive acoustics that we developed some skills also to not only to acquire, but to analyze such data collected by moving platforms, which is another challenge, right? Our longest mission took almost 140 days, I mean 139 days. In this mission, it was only related to one glider, right? It was one glider. It stayed like 139 days at sea. It dove more than 1,000 times. And we went through 1,746 kilometers in one mission. So it's huge. I mean, in terms of the reliability and the robustness of such equipment, we have a glider that performed more than 11 missions already, right? And since we also capacitate our team to do some maintenance on the equipment, we are able also to change batteries and to calibrate such equipment here internally at PROOCEANO, right? So from 2013 up to now, we already accomplished 2,568 sampling days. So when you compare the sampling days that we got with the gliders and the vessel usage that we had to perform this number of sampling days, you can compare and you can see the reduction of the cost that I mentioned to you prior, right? If in a regular oceanographic campaign, to sample the ocean, like to keep sampling for more than 2,000 days, it would cost a fortune, right? I don't know any project in the world with this vessel usage, right? So this was a game change in the oceanographic community, right? So on the last part of the presentation, I'll bring you some real data. I mean, I'll give you some flavor on what such equipments can collect, and which type of analysis and which type of new information such equipments are bringing for the oceanographic community, right? So as I told you, the transect that I showed you from the continental shelf break up to the deep water, I'm showing you here some results from 39 transects from March 2013 up to December 2014, right? So basically we were sampling this area, right? This is, I don't know if you can see my mouse. So here is Rio de Janeiro, right? And we were sampling here. This is an area where we have a lot of eddy activity, right? We have the Brazilian current flowing southwest, and with a lot of interaction with the bathymetry. We have a lot of sharing between the current in depth. So all those characteristics that it brings, they bring to the region a lot of variability, right, in terms of current. And such variability can bring risks to the drilling operations that are happening in that region, right? So by sampling that region, we could the glider normally it took to fly from here to here. It took more or less 10 days. The mean is 6.5, and the maximum it was 13 days. So this is important to check that to guarantee and to assure that this sampling, this transect, it's synoptic, right? So, and we can make a lot of, we can calculate a lot of oceanographic parameters from this transect, right? In this graphic, I'm showing you the timeline of the glider displacement from one point to the other, right? Okay, so when you do some calculations, one of the parameters that are straightforward to calculate from hydrographic transects, which are the data that the glider collects, is the geostrophic velocities, right? Now, this is an estimate of the currents from temperature and salinity, right? Basically, we are calculating the current associated with the mass field, I mean, right? So, and you can see the important thing here is that to get a picture, to get a seasonal picture like I'm showing you right now, it's very difficult. I mean, you have to have a lot of data to depict that, and with the glider, it's finally possible, right? And but this is statistics, right? When you, for example, another calculation, another analysis that we've performed, as I told you, this region, the main characteristic of the region is to have a shear in the first 1,000 meters of depth, a shear in the current system, right? So those currents, but normally they forget this. I mean, forget this word. They carry some water masses, right? So basically, evaluating the type of the water masses, you can depict what is happening in the ocean. I mean, in depth, right? Here we were tracking actually the limits of two water masses that are very, very much characteristic in the area, which is the South Atlantic center water and the Antarctic intermediate Antarctic water, sorry. So we were tracking the limits, the temperature and salinity limits of the water masses in time. So basically we were seeing actually this shifting, and we have, and looking at that, we realized that there was some moments where there was a huge shift, for example, in the mass field. I mean, it was like if the water masses that was supposed to be below the upper one, it shifted up. So it was a sign of something. Then we get into investigate it. And then we used to have also the glider, but also drifters and floats in the area. So when we took a look at the data set, we saw that the glider was flying pretty much in accordance with the transect that we draw. Two SVP drifters that we had in the area was like circling around something. And then when we saw the velocities, the geostrophic velocities at that time, we saw that there was a nice evaluation, right? And it was a sign that there was I don't know if you can see that this shift here and here, I mean, this one, sorry. You can see that this one on October 21st, and then you check here, you can see there was this shifting of this cold water into shallower regions. This is what we call, this was an eddy, which we call Cabo Frio eddy. It was the formation here in time of the Cabo Frio eddy, right? Which is an eddy of about 100 kilometers that from time to time it forms, it increases and it gets strong and then it shifts around, right? So those such features, it can jeopardize a lot the drilling operations because the current patterns shifted around. It could shift it around 360 degrees. So it's a mess for the operations, right? So as I told you here, in this time, we could depict what happened. But then there was another one, and we went to check. And then, of course, what should we do? Let's look at the other equipments to check and to evaluate what might have happened. And then when we saw the SVP was like drifting around, but also the glider was drifting around. I don't know if you remember, I told you in the beginning of this presentation, this equipment that we've been using, it has no propulsion, so it depends on the gradients to fly. So at that time, it was not enough to get rid of the current effect. So the glider was trapped by the eddy. So we could not, we cannot sample proper, the eddy, but we get a bigger scene on what happened, right? So as I told you, the main usage that we have for the glider is to improve our skills to diagnose and to forecast the ocean. So how we do that? So I told you that we've been using a lot of ocean modeling, right? So nowadays we are assimilating the glider data into the numerical models, not only the glider data, but also the profiler and also the satellite images. And in that way, we can correct the model forecast. And this is how I will briefly try to show you how we do that, right? If you see this slide, this is from the previous slide. This is this is a period very similar to that one. The eddy was forming, the Cabo Frio eddy was forming. And you see that there was a drifter at the sea surface circling around the eddy. And those graphics here, it shows the glider data when we cross the eddy, right? So you can see this is the temperature and salinity profile. You can see the isolines moving up as the eddy was growing stronger. This is called Ekman pump. So, and you can see from the other parameters, apart from the physical parameters, chlorophyll, scattering and dissolved oxygen and turbidity, you can see that there is a signature of the influence of the eddy into the distribution of such parameters, right? So this was such type of information was a game changer in the oceanographic field because previous from before the gliders, we could sample the ocean like this, but you need to keep the vessel there, and you need to be lucky to find the eddy, I would say. If you have the glider 24/7 at the sea, It's just the eddy to appear, and then you can go to try to sample. I mean, try, because it's not always easy, because as I told you, it's not easy to cross an eddy when you have a vehicle with no propulsion, right? So, but this is how we've been doing. So all these glider analysis and this operational oceanography, that field that we were developing here in Brazilian waters, we published a book into it was called Coastal Ocean Observing System. It was pretty much the work that was led in PROOCEANO by Francisco dos Santos, my colleague, which was leading the glider team at PROOCEANO. And it allowed us to actually use the glider in an operational basis and not only for research and rescue, right? So once we have depicted how we can analyze the glider data and how we can use it in terms of piloting and retrieving the data you need, I told you we've been trying to, we are also trying to assimilate such data into the models, right? So here is an example. This is another work done by another colleague of mine, Mauricio Fragoso. So in this project you have here is the ROM's free run in the left panel. So what is free run? We simply run the model without any forcing, I mean, without any assimilation, data assimilation, only the initial and boundary conditions, and let the model go, right? And you can see we had a drifter here, and the drifter was shifting around, right? But in our model, we could not see any feature. Actually, we could see a feature here, but it was displaced from where the drifter was pointing, right? So this is a common error in modeling, in hydrodynamic modeling, also atmospheric modeling. We have a feature. Your model has the ability to diagnose the feature, but not the exactly place where the feature is growing, right? This is one of the main errors in ocean and atmospheric forecasts, right? And one of the most efficient way to correct that is to assimilate data, right? Once we bring the glider data into the model and correct the model behavior where we have data, you can see that, and then we run again the model with the data. And then you see that the model starts to correct the very exact, not very exactly, but it's trying to correct the area where this feature, the eddy, was growing, right? And it allows you to get more reliable ocean forecasts by doing that, right? Just to have you some more, it's not actually, I didn't bring you numbers here for the comparison, but this is the graphic showing the black line is the drifter. It's our real world. The gray line is our model with 4D VAR assimilation scheme with the glider data into the model. And the dashed line is the free run of the model. You can see that when you compare the dashed line with the gray line, you see that once we assimilate the glider data into the model, you achieve very, very well results compared to the free run, right? This is for the zonal component of the current, and this is for the meridional component, right? So right now we are also using the glider, as I told you, to evaluate and to collect acoustic data, basically passive acoustics, right? We used such equipment in a project for Petrobras to evaluate the soundscape of the Santos Basin, right? Passive acoustic soundscape. You can imagine, it's not that difficult to imagine that to use a vehicle that is moving, actually is diving in the water, there's a lot of flow noise associated to that. So there's a lot of work to depict and to depict the data and to analyze the data in such a way that you get rid of this flow noise. So we did a lot of analysis on the velocities that we would need to dive and a lot of things to achieve good results. I will be glad to present such results in another opportunity, right? And this is really where we are going right now. We have another R&D project, which is the Projeto Azul Phase 2. It's ongoing. where we will combine gliders and ASVs, which are the autonomous surface vehicles. This nomenclature has changed recently. They are called MASS right now. So in this project, we will be combining the usage of a glider, of an underwater vehicle with a surface vehicle, but also to measure not only currents and the parameters that we were analyzing already, but also we will include waves measurements. And then also we will try to analyze ways to improve our capacity to assimilate data. So basically what we are doing right now, starting to do, is to analyze where the model is not so good, and trying to focus the sampling at that region to improve the ocean forecast, right? I brought you some pictures from the tests that we've been performing. This is the equipment that we chose. It's called sail buoy, right? It has an atmospheric station here, and it measures waves and sea surface temperature also. And also it has a sensor for hydrocarbon. So based on the sensors, we can also try to learn how to use it in a proper way. So as I told you, the way we work, we use the research and development projects to evaluate and to try and to test new technologies, and then we brought it into the real world to transform into services, right? So this is pretty much ahead. I apologize because I was like it was a long time since my last talk, so English was not so good, but thank you, obrigado.
Thank you so much. Thank you so much, Leonardo. So
there was some applause, but the mic was still muted.
Yeah. So thank you for the round of applause to Leonardo.
So I don't know if there are any questions.
Are we still able to ask questions?
Yes.
Okay. I have a question, which is, how is it that you manage to, so like the vehicle, the glider, from what I understood, it makes like a parable, let's say. When it goes, when it dives, it makes like a parable. It doesn't go straight down. How do you manage to keep the nose up in order to achieve that trajectory?
Not sure.
Hear the question?
No, not really. If you can,
okay. Yes. It's related to the movement of the glider up and down the water column.
I was asking, from what you told, the movement of the glider, it kind of makes a parable. So when it dives, it doesn't go straight down. So how does that mechanism work in order to achieve that trajectory? So to guarantee that it doesn't go straight down.
It has, first of all, the glider has a navigation model, right? So it takes into consideration the stress the vehicle is feeling when it dives also. I mean, the currents, right? But basically, the glider has a balloon internally, and there's a kind of oil internally, and it pumps the oil outside and inside to change its fluctuability, right? When it changes the fluctuability, it can dive or it can go up. Basically, it's this. Then you have the heave, pitch, and roll that can control the movement. So that's how it dives, and the displacement in the horizontal happens, right? Apart from that, it has a pinger and a lot of acoustic pingers internally. So it keeps pinging, and it the system knows the depth, I mean, approximately, because you feed the equipment with that. But there's a lot of, I mean, not only in this glider, in all the gliders, there's a lot of emergency mechanisms, but it's not unusual to have accidents. We already lost 3 gliders, right? We need to say that.
If I may, João, I have a question from the Zoom audience. It's from Anabela Oliveira, and she's asking if you have problems with nets and garbage in the sea.
Not net, but we believe that we had a shark bite in one of our gliders because we are operating very deep water, right? So we go, actually, we normally, in our normal case, we would be sampling from the continental shelf break up to the deep water. So risks, accidents with nets and everything, we already had with our mooring lines deployed in shallower water, right? But not with the glider, not that I remember. But the shark bite, it happened.
That's even more interesting. There is another question here on YouTube. I don't know the name of the person, but he's asking how, let me see. Yeah, I'm trying to translate in real time.
Yeah.
You started doing science, no? And but it's still, there is still a lot of technology developments for marine robotics in terms of science and technology. When did you feel that was time to set up a company that would use, I mean, gliders for modeling? That's basically the question.
Yeah, no, that's really good question, because when we start, I think I can speak from myself and from the others also. We were like trying. So we were actually already working internally at the universe to provide services for the oil and gas companies, because at that time, back in 2000, there was not many companies doing oceanography in Brazil, right? So there was a natural movement. So that's why we started to selling service as companies, right? And the reason that we brought the glider was the same reasons that we brought the drifters and we brought the profiler. It was because since we started from science, it was a natural way of thinking from us to keep close to the science development. So that's the way we flew as a company since 2000 up to now. So this is how we believe that a science-based company should work.
No, now I'm curious with that, and I've noticed from the beginning of this meeting, and then you just start, you are in the middle of your PhD, I mean, yeah, studies. So how do you link science in now that you have to come up with money for the company? This is very important for the students. How do you link science, technology in a way that you can still have fun imagining new things, but at the same time you make money enough to pay the people who work for you?
You already answered. I mean, I think in the way I see, you already answered the question. It's with imagination, because we need to develop, but we need to think where can we use this development, and this is the way we work. It's applied science by definition.
Yeah. Oh, sorry, João, I don't want to monopolize the discussion. Please ask the students if they have any other question.
Can I ask one question? The question is about, how do you prepare to lose vehicles? Do you account that in the company, or do you have insurance? What do you do when you think you are losing a vehicle?
Yeah, I mean, I would say that a big part of the maintenance we can do internally. I mean, we can change batteries, we can calibrate the system, we can, I mean, we improved a lot in the maintenance also. We have a team, a pilot team, and the maintenance team internally at PROOCEANO, right? In terms of insurance, it's very hard to insure such equipment, right? There's a lot of bureaucracy, and it's not easy to get such equipment insured. We already lost 3, and we were covered in 2 of them, if I'm not wrong. So it's not easy, and it's risky, but I would say that to pilot in a safe way, in an operational basis, there's a learning curve that you must face it, right? So as I told you, we've been flying gliders since 2013, and we are still learning. And right now we have some experience with different models, but I would say that it's the pilot team is not only good knowledge, a good oceanographic knowledge is important to pilot in the sea, because a good pilot is the one who will anticipate what will happen with the glider based on the current pattern, right? So so that's why we are still learning, but that's the way we've been doing.
Thank you. Any other questions? So I think in the room, here in the classroom, there aren't any other questions. So we'll thank you again.
So, João, can I ask another question?
Oh,
Sorry, you know, I'm saying that because I'm very enthusiastic of PROOCEANO, because I visited them last year in Brazil. Very interesting company. And how do you attract in Brazil talents for your company? Because it's very difficult to find, I mean, people involved on marine robotics and modeling in Brazil, as far as I know.
Yeah, I mean, it was worse when I graduated, but now it's a little bit easier. I mean, there's a lot of people in the university and looking for such area. I mean, here in Brazil, and I mean, what make us? I think what makes us attractive is actually exactly this link with the science developments, because it's. I mean, we are trying to prove every time that there is a way to sell applied science, right? This is what we do. So I mean, I talked to an oceanographic classroom last year in an internal project into the Rio de Janeiro State University, and I told the guys that. The difference between the student and a professional is only what you give up. I mean, in terms of the way you think. What I mean with that is that if things you started to do in college, you need to keep doing that. I mean, your concern with science, your concern to provide a good service, your concern to be in alliance and to be to be aware on what is being developed, I mean, internationally at that time. So you need to be connected. So by doing this, I mean, both the company and the employees or the people who is applying for that, it's easier. I mean, I would not pretend to be, I mean, posh here, but it's easy when you keep close to the developments. It's easy to attract people and to keep yourself in the edge of what is being provided as services. The limitation is money, of course, but it's then your ideas and your way of providing services is already attractive to not only to people who wants to work for you, but also to the clients. That's the way we see.
Thank you very much for your answer.
and actually, we have one more question here in the classroom.
Apart from oil and gas companies, what other types of companies may be interested in your services?
Good question, because the way we see the market is changing. I mean, and with all this situation in 2020, it's changing even faster. So wind farm market is another growing market that will be demanding oceanographic services and ocean services as well. We have also port authorities, not this type of robot, the glider, but another ones. So basically, every activity in the sea, in principle, will demand such technology and such services. It's just a matter of adapting to the spatial scale and temporal scale, right? This is the main question. I mean, in the oceanographic field, you need to adapt the equipment you have for the scales you want to solve.
Okay, thank you.
Okay, I think now we are done with questions here in the classroom. I don't know if there are questions in the YouTube.
No YouTube, not here. Yeah.
Okay, so I think it's time to thank Leonardo one last time. Thank you for your time.